Yeah, let us start with Hadi. So Hadi, first I want to ask you about the economical studies performed on smart grids. Can you give us more details about the if they did already life cycle cost analysis to know if it's profitable or not, and what is the payback period of such systems?
About the economics, honestly, we did not go over, we did not investigate the economic aspects of smart grid in detail to be able to answer your question. The literature review was already full and talking about the technologies and the smart grid in general. So if I would give an answer, it wouldn't be accurate.
Okay.
No, not look into the economics closely. But the only thing I can say is, like Jat was saying in the challenges section, that we should consider the high initial costs of transitioning into the smart grid versus the benefits that we would get from implementing them.
Okay, Tab, this technology is already implemented in some countries, no?
Yes, right.
Okay, in these countries, didn't they perform, you know that before implementing any project, we should know if it will, if it's profitable or not, and if it's not profitable, we'll not go over it, صح? يعني أكيد it will give us a certain profit. So in these countries, when studying the literature review, didn't you face any study that is clear showing the payback period, showing the performance of the system over its lifetime?
No, Sarah, we looked at, we found, among the articles we explored, there were many studies, but and we felt that the report is already too large to include these things. We considered adding this part. It's relevant, definitely, but it was already too extensive.
Okay, fine. Can you move down, please, with the slides?
Of course. Tell me you want to stop, please.
Yes, continue, please. Okay, down. Stop. Okay, previous slide, please.
This is the table. Which slide do you want?
The model one, the slide of the model.
The multi-agent control.
Previous slide, Hadi, previous slide. The one of the model, the suggested model.
Suggested model. Okay, the decentralized model.
Yeah.
Okay.
Next one.
Next.
Okay. Jad, can you please give more details about this model?
اوكي بس عم بيتاخر ليوصل عند السلايدز. اي رقم؟
It's fine. هادي ارجع على السلايد بليز. على سلايد الموديل هلا فرجيتنا اياه. Yeah.
Okay, the decentralized model. Okay.
The model suggested for smart grid is the decentralized model, as we can see. It's formed of nodes, and these nodes are connected in such a way, making this model like very efficient and resilient in case of electricity cutoff or a problem in the infrastructure. And it's basically formed of nodes that are independent and autonomous to make the model work autonomously, to make it automated.
Okay. Can you move down, please, with the slides?
Yes, of course.
Move down, please. Okay. Okay, continue, please. Okay, stop. Hadi,
Yes.
previous slide, please. Previous slide.
Okay, can you tell me just the title or the number of the slide?
I
Like
don't
في
see.
delay.
I don't see the number, Hadi. This is the problem. I don't see the number. Okay.
It's at the bottom right corner.
Yeah, but it's not appearing on my screen.
Oh, because of the banner. Okay.
Because of the box. Okay. Can you please explain in detail the scheme?
Okay, so this is basically the architecture of advanced metering infrastructure, which is the structure that connects different nodes in the smart grid. At the small level, we have the home area network, which is basically which consists of the local network of a residential building, for example, or in the case of an industrial plant or a power plant, would be a small local network. So it's the smallest unit in the smart grid network. If we zoom out a bit, we would get to the NAN, which is the neighborhood area network, which is a network of hands, basically. And if we zoom out a further layer, we would go to the wide area network, which connects multiple microgrids to a central entity. So basically, this is the three networks differ in scale, with the Han being the smallest network, and the one being the widest. Basically, this is all this picture is telling.
Okay, thank you, Hadi. Thank you. Okay, guys, we're done with you. Thank you. Next.
Thank you, Dr.
Welcome.
Yes, Professor, we can go next.
Yalla Mia, okay. Share your screen, please. Okay. Yalla, you can start.
Okay. So today we will be presenting how to harvest energy from piezoelectric applications. So our outline is the introduction, the research methods, science and developments, the limitations, and the results and future scope. With technological advancements, humans have become increasingly dependent on electronic devices and batteries. This resulted in a continuous increase in energy generation demand in the world. And these devices require energy and need to be charged continuously, which is not practical nor sustainable for our planet in the long run because this contributes to global warming. This introduces us to the core of our topic, which tackles the concept of energy harvesting that we're going to look at in detail in the few coming slides.
So portable electronic devices and biomedical devices became omnipresent in our everyday life thanks to their flexibility and ease of implementation. However, these devices are more or less limited due to their dependency on traditional rigid batteries that are the conventional source of power to most devices. And in the slide, we can see some example of electronic devices, pacemakers, and retinal prostheses as well. All of these devices require conventional batteries. Okay, now let's have a look at the caveats of conventional batteries. So first, they are known for their heavy weight, for their limited lifespan, since they have a finite amount of energy. They are also considered as expensive, and they may also have harmful effects on the environment because of their chemical composition. The replacement of these battery is considered to be expensive and a tedious procedure, especially if someone is located in an isolated place where they don't have direct access to the grid. All of these implies that the need to have a sustainable alternative power source for our portable devices. Now, the concept of energy harvesting consists mainly of exploiting wasted energy into useful electrical energy that we could benefit from. Riwa, please, next. This concept has been researched by many and studied for years in order to create self-powered and portable wearable devices that can operate by capturing the energy that is wasted to the environment without the need of an external power supply. As we can see, we have several sources of energy that could be exploited for energy harvesting. And some of these sources are the human motion, the natural resources, including hydro and wind power, mechanical energy, and biomedical energy. The principle behind the future of self-powered devices is called piezoelectricity. Actually, the piezoelectric effect is the capacity of a wide range of material to generate electric charge as a response to an applied mechanical stress. These materials have different structures, but all of them have in their unit cells lack a center of symmetry. And also they enable the conversion of wasted mechanical energy such as frequency, vibrations, and human motion into electrical energy. And we need to note that when mechanical stress is applied to these materials, the crystals inside, they undergo a deformation that will in return generate electrical current. Now, among the piezoelectric material, we have the quartz crystal, which is considered as the first piezoelectric material to be discovered. The atoms, as we can see in the atomic structure, they are equidistant from each other and from the silicon atom also. They have an atomic structure of a tetrahedron that contains oxygen atoms that have a negative charge and a silicon atom, which is the center atom that is positively charged. And this creates a dipole along each bond, and these dipoles can cancel each other out due to the symmetry. However, when the quartz is squeezed, the atoms shift, and because of the resulting asymmetry in charge distribution, we will have a net positive charge on one side and a net negative charge on the other side, and this results in voltage generation. Now, moving on to the research methods, researchers mainly focused on biomedical and piezoelectric shoe applications to explore and dive more into the field of piezoelectric energy harvesting. Starting with biomedical devices, we will focus on pacemakers, which are the devices that are very prominent devices in the life of many people. They are in fact small implantable biomedical devices responsible of contracting the heart muscle chambers to pump blood, and they also send electrical impulses to the heart to preserve a satisfactory heart rate. They are also very frequent and are usually used for people who have arrhythmia and also congestive heart failure. Pacemakers are powered by lithium iodine batteries that are usually used in pacemakers, and they have a lifetime of approximately 10 years. Removing and replacing these batteries each few years puts the life of the patients at risk because some complications might occur. Also, the cost of replacing these batteries is very expensive. So researchers wanted to improve the performance and the reliability of these batteries. This is why they wanted to have them to have their own power supply to become self-powered pacemakers. Now, the model under study consists of polyvinylidene thin film with a piezoelectric buccal beam array within a soft tube, as we can see in the picture below. This material, the PVDF, improved the power output due to its porous structure and biocompatibility with the human body, also to its electromechanical coupling efficiency. The source of energy in this design is considered to be an in vivo energy source. It's the heart or cardiac motion, which is considered one of the most captivating in vivo energy sources for harvesting cardiac energy. As we can see in the picture, the design is mounted on the pacemaker's lead, and the purpose of this design is to charge the pacemaker's battery by converting the mechanical energy generated from the cardiac pacemaker's lead into electrical energy. And in fact, the bending energy of the pacemaker's lead causes the deformation of the buckled piezoelectric beam, which results in the generation of an electrical current. Now, since the lead of the pacemaker follow a complex, the heart's motion, which is a complex motion throughout the cycle, the mechanical design has a complex motion from which two movements are responsible of generating electrical current, which are the vibration of the piezoelectric beams and the bending moment generated from pressing the beam. As we can see in the graph, the generated voltage due to the vibration effect is very minimal when compared to the voltage generated due to the complex motion. So we can conclude that the bending motion of the piezoelectric buccal beam contributes to the overall electrical output of the device. Now, the findings of this research are the following. Applying a pressure on the pacemaker's lead results in a power of approximately 0.9 microwatt and voltage and current of respectively 4.5 volts and 200 nanoamperes. And as we know, a typical battery of a pacemaker consumes around 0.78 microwatt per day. So we can conclude that the energy harvesting device is capable of self-powering itself with 0.9 microwatt for 1 day. Now, moving on to the power walk, we know that our lives as humans are powered by batteries, and we always feel like we're dependent on the grid and on that wire that always keeps us dependent. And our purpose of this study is to mainly cut this wire by finding new sustainable alternatives. And one of these alternatives is to capture the wasted power of human motion into the environment. The energy harvester design under the study is a piezoelectric shoe, whose role is to capture the human's potential energy, store it for later use to charge portable devices, for example. The piezoelectric material used here is placed where the stress and strain are mostly generated by walking, such as the soles and the heels. This device appears to be very useful especially for the people and the soldiers who are in military to charge radios, GPS units, and also night vision goggles.
Okay, so we identified and explored all of the piezoelectric applications leading to the harnessing of biomechanical energy from human as well as natural resources. But most importantly, we should be focusing on where to extract that energy from. So we should look at where the ultimate source of energy wasted is. We will be evaluating the various sources of motion from the human body in order to find out which part involved is the ideal one to focus on. Walking is the most frequent action our body follows through with. So we should explore how our body works by dissecting our motions according to each joint and muscle involved in the gait cycle or the walking cycle. These joints can perform positive or negative work. The positive work occurs when the muscle is contracting to perform the action, and the negative work occurs when the muscle releases after the action. Also, the work can be due to two things. The force acting through a linear displacement, which we will call W1, or the product of torque and angular displacement that we will call W2. We'll consider the following energy sources involved in the gait cycle, which are heel strike, ankle, knee, hip, shoulder, elbow joint, and center of mass. When taking the heel strike, for example, after placing small devices in some running shoes for motion monitoring, it has been proven that a great amount of energy is lost to our surroundings at the collision of our heel to the ground, while the rest will remain as elastic energy inside of the shoe's sole. In fact, the heel strike makes up 20% of the gait cycle. When striking our heels to the ground, we displace a force perpendicular to the ground that is around 1.2 times our weight and create a work of type 1. To be able to profit of this wasted energy, the user could wear something similar to the piezoelectric shoes shown previously. The combination of bodily movements derived from the ankle, knee, and hip joints constitute what we call the leg motion. In this motion, we are displacing a torque as we are moving in a 3D plane. So it's generating a work of type W2. The torques that affect us the most are the ones acting along the sagittal plane, which splits our body longitudinally across our center. In the graph below, we can see the difference in outputs between the ankle, knee, and hip joints throughout the gait cycle. And in the table, we can see that there are 4 distinct phases throughout the gait cycle. We can also see that some average energy values are positive while others are negative, and this will depend on the type of work they conduct according to the different phases. There is mostly negative work outputted from our lower body and specifically from our knees. If you look at the graph, second column, sorry, and the third row, you can see that there is the greatest amount of negative energy from the knees. Actually, they use up 90% of their total energy as negative energy. It would therefore be smart to design a device that we could implement or wear on our knees, especially for amputees that could benefit immensely from integrating a piezoelectric device that can harness energy from small bending moments into computerized prosthesis, which usually consume less than 1 watt per day, but require charging on a daily basis, which is why it would be ideal if they were self-powered and sufficient. Arm motion is commonly left out of the walking cycle, but it's very important to note that most people swing their arms when walking, so they produce energy even if it is a small amount. It can be split into 2 motions, the relative motion between the forearm and the upper arm, so the change of angle at the elbow, and the relative motion between the trunk and the upper arm, so the change of angle at the shoulder. So when taking into account our center of mass releases deep motions vertically as well as horizontally along the ends of our body. On top of our stripe movements, our center of mass motion could be subjected to an external force, such as the load of something we may be carrying. Having both of these motions in sync creates a relative motion between the user and the external mass they are carrying, but more importantly, it increases and eases the harnessing of energy from displacing ourselves throughout the gait cycle. We could harvest this energy throughout the use of a backpack, which we can see in the figure, where energy can be generated by attaching the green tooth rack to the load plate that will mesh with the pinion gear mounted on a generator and therefore create electrical energy. Unfortunately, this design would increase our weight, hence our metabolic cost. So harvesting negative work is more effective than harvesting positive work because the latter type of work increases the metabolic cost. And the metabolic cost is the amount of energy required to perform an action. Even when it comes to negative work, it is important to compare the metabolic cost of harnessing energy from the different joints. The most important parameter we should take into consideration is, of course, the efficiency of the device. The metabolic cost gathers two kinds of energy, the energy spent by the electrical power and the energy spent by carrying the harvesting device, which ideally should be made out of a light carbon fiber material and designed to the highest optimizing level. The cost of energy harvesting is far less than the cost of carrying batteries with us, which will affect our center of mass instead of a simple joint that will hardly feel the device attached to it. Now, in addition to human resources, we can also use natural resources in order to harvest energy. Piezoelectricity can be employed for practical kinetic energy harvesting owing to its high power density. Natural and most importantly, renewable resources such as water, wind, and wave motion, in addition to their harvesting via piezoelectricity, have been intensively evaluated in the recent decade as the most widely dispersed kinetic energy sources. Okay, so for wind flow energy harvesters, energy is harvested and captured from flow of fluids such as wind and water through the conversion of the fluid motion into rotational motion and vibration. Windmills could be redesigned into piezo windmills by integrating a piezoelectric device in it in order to harvest this natural energy. This piezo windmill proposed would function according to excitement induced by rotating magnets that could still harvest wind energy at low speeds, contrary to the common design we are used to that only gives an output at high wind speeds. So this edited model could provide increasing levels of energy that we could capitalize on, as the wind is never non-existent, only dampened. We can also edit this model by linking a Scotch yoke mechanism, as we can see in the figure, to a classic wind turbine, which will then be able to convert the usual rotational motions received into linear vibrations that will be displaced with the help of the springs located inside into the lever and finally reaching the piezoelectric bar. There exists low frequency vibration in liquid bodies such as and profit of them. This is where the magnetically coupled nonlinear bistable piezoelectric device seen in the figure above comes into play. The wings that you can see will be flapped, and they will be flapped through the vibrations of water, and they will excite the magnets, leading to an amplified force reaching the piezoelectric layer through the flex tensional structure. And this structure can easily be placed underwater and is capable of collecting and harnessing energy from low vibrations, contrary to dams that would require greater velocities from the widespread fluid. So this model can be improved like the previous one, and it can be improved by involving a piezoelectric lever system that is located within a cylindrical energy harvester that will convert the surrounding low frequency vibrations into high frequency vibrations that can be dissipated through springs and levers until reaching the piezoelectric bar that will finally convert the kinetic energy into electric energy as seen in the figure below. Rainwater is considerably harder to reunite into a uniform body that will present consistent vibrations than ocean water or seawater. So ideally, it should be first collected before we can do anything with it. We can harvest energy from rainwater through two methods. It can be done by collecting the kinetic energy instantaneously upon impact on a piezoelectric cantilever beam, or by collecting the potential energy after all of the rainwater has been combined into a control body and then flipped onto a baffle plate and the piezoelectric element, as we can see in the figure. Now, the second technique is better because in the first one, there are a lot of droplets of rain that we are missing, and it's not very consistent. And in the second one, we can create our own motion and give it its own velocity.
Now, moving on to the PaveGen, which is a clean, sustainable energy harvester. The climate change and the growing universal demand for energy, in addition to its scarcity, are the main reasons why Lawrence Campbell Cook decided to come up with the PaveGen concept, which is the invention of a clean, eco-friendly, and off-grid electricity by using the power of a human footstep. The design consists of a kinetic floor tile that captures the power of a human footsteps. And the tiles consist of three main components, which are an electromagnetic generator, a single triangular composite tile, and the human footstep. The slabs underneath the floor tile needs to be compressed by only 5 millimeters in order to harvest energy. The main goals of this design is to generate green, eco-friendly off-grid electricity and to use electricity in emergency, as well as generate power for the use of smart data sensing. Now, the power generated, these tiles are electromagnetic. So when the people step on the tiles, their weight will result in a vertical displacement of the electromagnetic induction generators, which will lead to a rotary motion that will in return produce power. Also, based on findings, 250,000 footsteps could charge up to 10,000 mobile devices. And after some calculations, the power generated over a PaveGen lifetime is estimated to be around 11.6 megawatt hour. Now here we can see the PaveGen models. We can see the triangular tile. We can see the process, how when a person walks on the tiles, it directly generates energy, and we're capable of charging the batteries.
Now, after discussing all of the benefits, it's important to go over the risks and safety these technological advancements could have on the user's well-being if not used, or more importantly, installed properly. The most common electrical hazards the human body faces are thermal hazard, shock hazard, short circuit hazard, and microshock sensitive. These risks are not limited to the use of the proposed devices, but could seriously harm the user's body in some cases. By passing through circuits, electrical energy is converted into thermal energy, where it could lead to some hazards such as short circuits, melting wires, or igniting nearby materials. So we should always be aware of that in these applications. Shock is a result of electrical currents passing through one's body that is highly conductive, specifically reaching their heart and putting it into fibrillation, similarly to what a pacemaker does to keep the heart beating normally. So we should know that most of our body's resistance is located in our dry skin. Our insides are far less resistant and more prone to conduct the shocks that may have bypassed our resistive skin barrier. So if a person is exposed to a pacemaker lead, for example, then they are what we call microshock sensitive. The type of piezoelectric material used is extremely important, as some of them are laced with lead, making them extremely toxic to our bodies. Piezoelectric zirconate titanate, also known as PZT, displays advantageous yields through its superior performance, but it is a lead-based material, making it very toxic, and we can't use it in medical applications. All of the materials covered in the research that we have done are lead-free because of their mostly medical applications, except for the one used for the water flow harvesting. These new materials that are mainly made out of ceramics have proven to display electromechanical and thermal and mechanical performances that are extremely competitive with PZT, if not better. Now, when talking about the safety of harnessing energy through piezoelectric applications, we must take into account the two types of devices we could use to harness energy. One would be wearable and the other would be implantable. And it's crucial to make sure that the implantable devices do not cause us any harm. There is a great number of people that now require special implantable and electrical devices to function on a day-to-day basis, such as pacemakers or prostheses. As discussed in the beginning of our presentation, these devices run on batteries and are either frequently rechargeable or have to be surgically replaced when their batteries run out. So the second option is much more dangerous, as there are more risks when you are being operated on, no matter the succession rate of the surgery. And by replacing these devices by lead-free piezoelectric devices, we are limiting the risks of not opting for this new technology. Also, to be on the safe side, we could choose to wrap the foreign piezoelectric device in a biocompatible material such as polyamide to decrease the risks of a failing device in case it is rejected by our immune system. So to conclude, we know that now that we can harvest energy from human and natural resources when it comes to piezoelectric applications. We should always aim to have a minimal metabolic cost based on negative work. Our lower body generates and wastes the most energy, and our knees specifically do that on a short scale, while on the big scale, we should focus on natural resources as energy generation. And there is always room for improvement no matter the devices. And as a future scope, we should aim at making piezoelectricity more common in third world countries to meet the high energy deficient demand, especially in Lebanon. Thank you.
Thank you. It's very interesting and it's a nice presentation. Can we please go back to the slide?